Good evening, ladies and gentlemen. How's everybody tonight on this really balmy evening? Doing well? Good. As you know, my name is Mark Razzie from the Public Services Office. Just wanted to thank you guys all for coming out tonight. In 1952, a group of American scientists decided the world scientific community should undertake a third International Polar Year, or IPY. Building on those carried out in 1882 through 1883 and 1932 through 1933, the idea of launching an artificial satellite took hold during the IPY, and the event was renamed the International Geophysical Year, or IGY, which then took place from 1957 to 1958. The IGY's Earth satellite program led to the Soviet Sputnik surprise, and then, of course, the space race. It also led to the transformation of JPL from an Army weapons laboratory to NASA's Planetary Exploration Center. These events revolutionized American science, literally creating the new field of planetary science while enabling new discoveries in areas as diverse as geophysics and climate science. Tonight's speaker is uniquely qualified to tell this story, being the historian at NASA's Jet Propulsion Laboratory. He's the author of 2 books, Blind Landings, Low Visibility Operations in American Aviation, and High Speed Dreams, NASA and the Technopolitics of Supersonic Transportation. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Erik Conway.
Well, hopefully this microphone, I can hear myself. All right, good. Thank you all for coming out tonight, Thursday night, to hear a historical talk. Most of the speakers in this series, of course, are coming to tell you either current science or current launch news. And so this talk is going to be a bit different. The real trigger for this talk is that this year happens to be the 4th International Polar Year. And so we at JPL thought it might be good to do a bit of a retrospective on what the 3rd International Polar Year, what we all now call the International Geophysical Year, actually did for us. And I'll make no claims that the 4th Polar Year will be anywhere near as spectacular, but I do want to talk a bit about what I see as being a revolutionary period in American science in the 1960s. So first, let me talk about the IGY. Okay, the button that says press for slide change doesn't cause a slide change. Okay. So the International Geophysical Year was an 18-month period between 1957 and 1958, during which 40 nations, scientists, participated in very large-scale experimental and observational studies devoted to better understanding the Earth and its processes. As I've said, it wasn't the first international year devoted to science. There had been 2 previous international polar years. The poles were important to these generations of scientists largely because they were considered to have very powerful influences on the weather, and weather is both of great scientific interest at this time, as well as being of considerable economic interest. The U.S. Weather Bureau is one of the oldest science agencies in the United States government for precisely this reason. The dominant meteorological hypothesis of the era was known as the polar front theory, that lasted well into the late 1930s. And the second polar year resulted in a permanent ring of meteorological stations around the Arctic, but not the Antarctic, intended to help better foster weather forecasts in the Northern Hemisphere. This map is the Arctic stations established during the first International Polar Year in 1882. Now, the International Geophysical Year. These 3 are a product, really, of these 3 gentlemen. The idea of carrying out the 3rd International Polar Year first came up in 1950 in the home of James Van Allen. James Van Allen is the young guy looking at you on the far left, who hosted a visit at his home in Maryland of the British geophysicist Sidney Chapman, discoverer of the ozone layer. Sidney Chapman is the guy in the middle. Lloyd Berkner, a physicist who is also very well connected to the science political establishment in Washington, is apparently the one that suggested that they go beyond doing a 3rd polar year and focusing on the larger issue of Earth-scale geophysicists. So by the time the formal proposal was made to the U.S. National Academy of Sciences and to the International Congress of Scientific Unions, often referred to in science circles as the ICSU, in 1952, their goals had expanded dramatically to encompass the entire Earth. Now, the reason they made that proposal to encompass the entire Earth was because of the Second World War's technological innovations. There were a lot of new technologies available with which to study the Earth. And a principal one is these critters, rockets. There are 3 here. The one on the far right is from our competitor, the Applied Physics Lab in Maryland, called the Viking rocket. This is a sounding rocket that was active by 1946. The one in the middle, of course, is the German V2 with what's known as a Watt Corporal mounted on its nose. That's a 1949 image. On the far left is a JPL rocket, the Watt Corporal itself. Posing with it is one of our founders, Frank Molina, a student of Theodore von Kármán's. There's another set of technologies I haven't gotten pictures of because they wouldn't be terribly revealing, of radar. Radar was very important to studies of the high atmosphere in the 1940s because you couldn't reach the highest portions of the atmosphere with balloons, but these new devices, rockets, could get into interesting new phenomenon. Furthermore, Lloyd Berkner especially knew that there had been a lot of studies in the late 1940s done of the possibility of actually putting a spacecraft into Earth orbit. Lloyd Berkner was the driver of this shift in policy. This particular image I pulled off the cover of one done in 1946 by what's now the RAND Corporation, at the time was called Project RAND, and was a subsidiary of Douglas Aircraft Corporation in Santa Monica. The title of this report was The Preliminary Design of an Experimental World-Circling Spaceship. Scale's a bit off for that period in time, and I always find interesting looking through this that they decided on a bullet shape. Pretty much no real rocket that I'm aware of used that shape, but it became common in science fiction writing throughout this period. Now, I don't want you to get the impression that this talk is just about space stuff, though. Equally important to my purpose is another one of the International Geophysical Year's activities that was much, much smaller in scope and in finances, that was pitched to the U.S. Committee for the International Geophysical Year by the oceanographer Roger Revelle. That's him on the right. Revelle had been involved in a long-running argument with a geochemist by the name of Hans Suess and some others over whether the oceans were absorbing all of humanity's carbon dioxide emissions or only 99%. He wanted to hire a new Caltech PhD named Charles David Keeling, that's Keeling on the left, who just invented a super accurate method of measuring carbon dioxide in the atmosphere. And Keeling wanted to run around, Revelle wanted Keeling to go run around the world measuring it very accurately in lots of places. Revelle thought this would make a database to which measurements 50 years in the future, this year's 4th International Polar Year, would be able to compare them to. Now, Revelle thought that CO2 amounts were going up so slowly that you'd need 50 years to measure a change. Keeling didn't believe that, but Keeling was a very small minority. Most other geophysicists at this time believed that the oceans absorbed all humanity's carbon emissions, and therefore Keeling would wind up measuring a flat line. Keeling also only wanted to measure in one place. What Keeling was really hoping he could measure was the diurnal respiration of the lands around the measuring site. As many of you know, plants have 2 different respiratory cycles. They make oxygen at one point in the day, and they make carbon dioxide in the other. And he hoped to be able to measure that diurnal cycle. So he wanted to stay in one place and just measure at Mauna Loa. That was a much cheaper proposal, and so that's the one that was funded. Now back to our satellites. As far as the U.S. satellite program went, there were 2 real contenders. The Naval Research Laboratory over in Annapolis, proposed Project Vanguard using a rocket based on the Viking first stage, a rocket called Aerobee, which is a derivative of the Watt Corporal I showed you earlier, and a new 3rd stage solid rocket. This they claimed would be able to orbit a 25-pound satellite, spherical shape. Werner von Braun's group down in the Army Ballistic Missile Agency in Huntsville, Alabama, though, proposed Project Orbiter, which would use a Redstone first stage. That's what you saw on the bumper whack earlier. A second stage composed of a cluster of 30 JPL solid rockets called Loki. They were about yay big. And a third stage 7 of Loki rockets, and a fourth stage using a single Loki with a 5-pound satellite. A committee led by JPL's Homer Stewart, who died just a few months ago, actually. And let's see, is this pointer working? That's Homer Stewart right here. This is Lee Dubridge, the president of Caltech, and JPL director William Pickering at the award of Stewart's 25-year pin. Homer Stewart's committee looked into the subject of which would be the better proposal and recommended the Naval Research Lab's proposal, largely because of its allegedly greater payload weight. Stewart never agreed with the recommendation. He thought that there was far too much technological development that had to go into the Vanguard project's rocket, whereas the JPL ABMA proposal was much more mature, but he lost. And Vanguard's proposal went ahead. So Project Vanguard and its 25-pound payload was enough to carry a small radio and a set of small experiments. The U.S. National Academy of Science actually formed a committee to select the payloads. They actually assumed they would launch about 16 of these satellites over the course of the International Geophysical Year and a little bit afterwards. So they selected about a total of 40 different payloads, funded about 25 to completion, in hopes of having lots of experiments go into space. Meanwhile, while that project's going on, JPL Director Pickering and Werner von Braun went to work on a very highly classified set of tests on a reentry vehicle. These haven't gotten enough attention, so I want to bring out that these were the true root of the team's eventual success in the space race. The project was called the Reentry Test Vehicle, and this picture is of the Reentry Test Vehicle stack in September 1956. The purpose of this was to demonstrate an ablative heat shield method of reentering warheads into the Earth's atmosphere. The Army wanted to be able to use this on nuclear weapons on ICBMs. The Army needed to know whether this reentry method would actually work, so Huntsville and JPL built a dozen of these test vehicles using Redstone first stage, and they switched the upper stages to use a cluster of scaled down Sargent solid rocket motors. These were larger and more powerful. They would lift a warhead-sized test vehicle, complete with low-power transmitter and floats so that it could be covered from the ocean to an altitude of more than 600 miles, but would not reach orbital velocity. Now here's a set of pictures of the reentry test vehicles warheads. Notice that there's a key difference between these three setups. This is actually the first launch. Notice that it looks a lot more like a spacecraft than this one, because that's what this was for. This is actually the Project Orbiter configuration that was originally proposed. The JPL folks had this design done first, so it was flown first to test the radio and tracking systems. This second setup is actually the reentry cone. This is the image flown on the second flight, which is in 1957. That flight was technically a failure because the guidance system of the vehicle failed. However, the warhead was still tracked to impact, but it wasn't recovered. It sank. There's some speculation, actually, that its float bags were bitten open by sharks. Believe it or not, because the third flight worked perfectly, when they fished the warhead out of the ocean, sharks had in fact bit its float bags but didn't penetrate, so they were able to collect that one. So this had flown now 3 times by the middle of 1957, and General Medeiros, the commander of the Army Ballistic Missile Agency, decided to terminate the program. It had shown that the ablative reentry method really did work. It worked better than expected, so he was quite happy. Meanwhile, the Vanguard project that was supposed to be the U.S. entry into this space race was having endless troubles. The majority of the contractors' workforce was reassigned right after they won the contract to the Air Force's Atlas ballistic missile program, which had higher priority. And the leadership had to start basically from scratch, training new people. Many design assumptions turned out to be optimistic, as Homer Stewart had thought, and the rocket got further and further behind schedule. So that's what gave the Soviets the opportunity to be first in space. In 1957, this little object, Sputnik 1, is orbited by the Soviet Union. Truly a shot heard around the world. JPL director Pickering was in Washington at a reception at the Soviet embassy when this happened on the evening of 4 October, when he was told by the renowned science journalist Walter Sullivan that the Soviets had just claimed to have launched satellites. So Pickering wandered off to the International Geophysical Year offices nearby to find out whether it was really true. There was some radio equipment, there was more in Pasadena. It took them a while to figure out when it would fly over. They initially got the calculations wrong, but there was a Sputnik. It really did happen. That same night, von Braun happened to be having dinner with General Medeiros and with the Defense Secretary, Neil McElroy, and yelled, "Vanguard will never make it," von Braun said. "For God's sake, turn us loose and let us do something. We can put up a satellite in 60 days, Mr. McElroy." But McElroy knew that the White House didn't want an Army rocket to be first into space. The White House wanted Vanguard to try first, so it was scheduled in December 6th. However, President Eisenhower did approve a backup, so Medeiros pulled out of storage one of the reentry test vehicle stacks and had remanufactured one of the early configuration, the first configuration I showed you that looked for all the world like a satellite. And now I forgot to tell you already, let's see if this will work. So that was Sputnik 2. That was the first Earth critter in space, Laika. As a 2,000-pound vehicle, much larger than anything JPL, Vanguard, or anyone else could do at the time. And this was an even bigger shock to come in December. So who would build the satellite? That was not initially decided. It was argued over. Von Braun, of course, wanted to build the satellite, along with everything else. JPL wanted to build it. But Pickering was able to convince General Medeiros that because of JPL's superior electronics capability, we were building the tracking systems as well as the instrumentation for these things, that JPL should build the satellite. And so that went ahead. This picture is a mock-up built later. I know it's later. I don't actually have the date for this picture, but that is the headquarters building here at JPL, and that's not built until 1962. So it wasn't there. This again is Pickering and von Braun. So this is Vanguard's first. What is this? Playing the file may result in unexpected behavior. I didn't ask it to play anything. There's nothing on that slide to play. I hate Microsoft. Okay, so there's nothing there to play, so don't worry about that. This is what's known as, often called Flopnik in the space history business. This is Vanguard's first launch attempt. You can see it didn't get very far. It got about 4 feet before the engine shut down. It fell back on the pad, exploded. The object you fall falling off the side there, you can see the nose cone falling off. The satellite actually comes off, bounces to a stop, and they pick it up. It still worked, but they decided it was too damaged to refurbish and try again. So it's hanging now in the National Air and Space Museum in Washington. This, of course, was JPL's main chance to get out of the weapons business, as many of its people wanted. And so maybe this is the one it won't play. Oh, that's bad. Okay, well, I was going to show you the launch of Explorer 1 and all the nice Army music and so on, but I guess that I won't. That's too bad. So on January 31st of 1958, JPL and ABMA launched the first American satellite into space. This was a scientific mission that had its very small instrument package in it from James Van Allen. And let me show you the data strip that it sent back. This is not a QuickTime file, so it should work. Yay. Okay. So what are you looking at? The instruments that Explorer 1 took with it were for skin temperature. That's this. You can see that they wrote in it's about 30 degrees Celsius. Nose temperature. Skin temperature, nose temperature is a bit warmer. There was a meteorite detector on it. The engineers wanted to know what micrometeoroids might hit it, and so there were 2 different sensors. There was a microphone listening for impact, and there's also a set of wires that were spaced so that they'd be broken by meteorites of certain size. And here's a data chart showing meteorite impacts. And this last one is Van Allen's famous cosmic ray instrument. You see the cosmic ray counts varying widely. Eventually, after a few days of this data, he concludes that what he's looking at is the instrument saturating at certain parts of the orbit, and it thus far exceeding its measuring capabilities. He eventually develops the conclusion out of this that the Earth is surrounded by these high-intensity radiation belts that now bear his name. The Soviet two satellites never published any real science, although it turns out that they did carry instruments for this, but the Soviets, for reasons that my other Russian historian friends haven't quite figured out, they never do anything with the data. The Soviets are always interesting. So there was lots of hullabaloo after this. After the Explorer launch, President Eisenhower had to make decisions about who would control the nation's space capabilities. The Army had succeeded in reaching space, but it made little sense even to General Eisenhower, who was an Army guy after all, to own this technology. He thought the Air Force should own that. The Central Intelligence Agency ought to own data collection, or rather intelligence collection from space. And even the Navy, he thought, had better claims on military space capability. He also had to consider the public impact. Sputnik had caused, the Sputnik scare had put an enormous amount of pressure for good performance on the US space program. And he thought that a military and thus classified space program would not produce the public space spectacles that seemed to be required. So instead, he decided to take a very small agency at the time, known as the National Advisory Committee for Aeronautics, and transform that civilian research agency into this new civilian space agency. This bill was dispatched off to the Pentagon for its review in March 1958. It reached Capitol Hill in April. It took a few months to argue it through all the committees that were interested in it, and it's finally signed the 29th of July. That didn't clarify what to do with JPL and the Army Ballistic Missile Agency, though, because both of them belong to the Army, and that required further negotiation. So what to do? Well, there's a question even here at JPL over what role it would want to play. It was pretty clear that Pickering and also Lee DeBridge, the Caltech president, no longer wanted to be doing this weapons work. Pickering had originally been a cosmic ray researcher, and he wanted to get back to that. So he called a staff meeting of his senior leadership here at the lab and put out a question, what do we want to do if we join this civilian space agency? And after some arguing, they came back to say that they wanted NASA, or excuse me, JPL to be converted into a planetary science laboratory. And they had various reasons. They figured that Earth orbit would soon be very crowded. Obviously, the Defense Department was going to be launching a lot of stuff up there. The Air Force did all of its ballistic missile and space stuff through contractors, and those private contractors would be able to raise a lot more money for technology development off private capital markets than JPL as a nonprofit ever could. So they figured that they'd go into the one area that probably wouldn't draw lots of corporate and even internal NASA interest. NASA was clearly going to be focused on human spaceflight. So they decided to send Pickering to Washington to advocate getting JPL transferred to NASA and made a planetary center. He found that Keith Glennon, that's him on the left, also wanted to take JPL away from the Army, so that turned out to be an easy negotiation. The Army even was willing to let it go by this point, figuring they were better off trying to keep their hands on Werner von Braun for a while longer, and that's what they did. The ultimate agreement had JPL transfer to the Army almost immediately in December of '58, while the Army Ballistic Missile Agency stayed in the Army for one more year. So we left our friend Dave Keeling back on Mauna Loa in 1958. So let's talk a little bit about that thread of the story now. Keeling measured carbon dioxide content of the atmosphere 4 times a day, every day, for the International Geophysical Year, a job that I would find unspeakably boring, but apparently not him. And in 1960, he published the first of his series, what I consider a seismic scale shock to the beliefs of the American scientific community. The first shocking thing about this chart is it clearly showed the respiration of the biosphere of the northern hemisphere. This is published in TELUS 1960, as you can see. Most scientists had assumed the atmosphere's CO2 content was so large compared to what the biosphere could respire that you wouldn't make a measurable change. Well, that was wrong. And this was probably the larger shock. His data showed a trend in carbon dioxide increase already after only 18 months of about 1.5% per year, not per decade as Roger Revelle had thought. Only a steam engineer by the name of Guy Callender in Britain had thought this is even remotely possible. That's the only evidence that we can find in the published literature anyway. And what geophysicists would believe a steam engineer. So by 1965, Keeling kept measuring. He had shown that this trend was real. It wasn't a measurement error. It wasn't a one-time fluke. This is his curve as of 2005, the year he died. Keeling showed that humans were changing the chemistry of the atmosphere and doing it rapidly. Carbon dioxide had been identified as a greenhouse gas in the middle of the previous century by an Irish physicist named John Tyndall. So Keeling's evidence raised some obvious questions. How much would rising carbon dioxide levels matter? How much would they change the Earth's climate, in other words, and how fast would they do it? By 1965, the year I was born, Lyndon Johnson, the president then, sent this special message to Congress. Air pollution is no longer confined to isolated places. This generation has altered the composition of the atmosphere on a global scale through radioactive materials, above-ground nuclear weapons testing, and a steady increase in carbon dioxide from the burning of fossil fuels. Nowadays, we call this global warming. The term hadn't quite been invented yet, but this kicked off interest in this whole subject of chemistry and Earth's climate. Now, that's one thread of the story, and I want to take you back to the planetary stuff. Looked at slightly differently, what Dave Keeling had shown was the importance of chemistry to geophysicists. Chemistry had been seen as relatively unchanging to this point, and thus not very interesting. If you're a scientist, do you really want to keep trying to measure something that doesn't change? What does it tell you? It's not very career enhancing. So there was no interest. What I still don't understand is why Keeling thought that all of this was wrong and worth his time. And I'll never know the answer to that since I can't ask him. Keeling had shown that this belief that chemistry was unchanging on Earth was wrong. And so too did JPL's first interplanetary reconnaissance missions. By the end of the 1960s, I hope I convince you, they'd radically changed our understanding of the inner solar system and the linkages, again, between planetary chemistry and climate. Now, in 1960, this guy, and a meteorologist by the name of Will Kellogg, chaired a conference here at Caltech on the atmospheres of Mars and Venus. This, of course, is Carl Sagan. This picture is actually about 1971, 11 years later. At this point, Venus, 1960, recall, was largely seen as a slightly warmer Earth, possibly with global jungles. There was a minority thesis that it had a global ocean. However, there was also a minority thesis that it was incredibly hot. And Sagan actually believed this on the basis of some radio telescope data that had been collected in the last few years. He had formulated a hypothesis that this was the result of an extreme greenhouse effect, and that these temperatures could be well above 500 degrees Fahrenheit. But he was a new guy. Most scientists don't listen to the new people until they've made quite a case. But Sagan thought you could make an instrument for even the earliest planetary spacecraft that could find out whether it was, in fact, this planetary greenhouse causing this absurd reading, or what many people thought was absurd, or whether it was a very hot upper atmosphere with a much cooler surface that could still support life. At the same time, most scientists in this era were convinced that Mars had life. It had plant life anyway. They didn't any longer believe in intelligent life, really. An annual wave of darkening that traveled across the planet was interpreted as the effect of Martian spring. Just as Earth has seasons, Mars does too, and blooming plants would change the surface color. While we couldn't see the plants from here, you could see the change in the reflectivity of the surface. Plants could be lichen, of course. They could be our kinds of plants, but they could still have this effect. So the first Venus-bound spacecraft got an instrument by the name of Frank Barath to measure the microwave intensities that would hopefully confirm or deny Carl Sagan's hypothesis, while the first spacecraft to go to Mars primarily had cameras. Here is Mariner 2, the first American spacecraft to reach Venus. One Mariner 2, well, Mariner 1 wound up in the bottom of the ocean. We had this problem with rockets a lot in the early 60s. Reached Venus in 14 December 1962. Due to Venus's cloud cover, which is planetary in scale, you cannot photograph anything, and that's why I don't have a picture of the thing for you. It did prove that Venus is incredibly hot, with an atmosphere about 300 times as dense as the Earth's. And it also showed that it's the surface that's that hot, not the upper atmosphere, as the other alternative hypothesis had said. Its instruments showed that Sagan's runaway greenhouse effect was roughly true. It's not completely accurate. There's been lots of work done since then, but that dense atmosphere had roasted the planet. It gave the planetary science community an early object lesson in the relationship between chemistry and climate. For the next decade, there are lots of model studies trying to investigate how a planet that's so superficially like Earth, it's almost exactly the same mass, it's not actually all that much difference in terms of the amount of sunlight that reaches the top of its atmosphere, could become so dramatically different. Here on Earth, carbon dioxide, for example, is removed by a geologic process involving liquid water and rock. The result is the one method of producing carbonate rocks. This has caused Earth to slowly cool over the eons. On Venus, it sure looks like that process never got going. This meant that conditions that life like ours could form under were much narrower than the scientists of 1950 had thought. Now Mars, we had a Mars mission in flight by 1964. This is it here on my right anyway. And we got to Mars in, 1965, and I can't believe I didn't put down the date. Sorry. It returned about a dozen shocking images as well. We had already known that the Martian surface was cold, but not as cold as it turned out to be, and that the Martian atmosphere was thinner than Earth's, but again, not as thin as it turned out to be. Virtually no one had expected this cratered landscape. It demoralized a lot of scientists because the place looked like the moon. The moon we already knew was not living by then, and this gave lots of people pause, thinking that, well, maybe Mars is just as dead as the moon. There were 2 more flyby missions to Mars in Mariner 6 and Mariner 7. Mariner 4 was successful enough to get William Pickering invited to the White House. Presenting some of these images of Mars. This is Pickering. This is President Johnson. This is Jack James, who is the project manager for Mariner 4. So the last of the planetary spacecraft I want to talk about is JPL's first orbiter. We kept that the unexpectedly hostile red planet this time. And Mariner 9 was the first spacecraft, I said this already, originally known as Mariner Mars 1971. It arrived 13 November 1971. In this picture, the propulsion system that slows it to go into orbit is sitting on top of a vehicle that otherwise looks a whole lot like the one you saw earlier in Mariner 4. I'm told by the structural people that they didn't have to strengthen the structure of Mariner 4 to make it into Mariner 9 because they had so grossly over-designed it. Just an early example of the way JPL over-engineers everything. Mariner 9 is probably famous because it encountered Mars in the middle of a planetary scale dust storm. This hadn't really been understood from Earth as Mariner 9, and there was an accompanying Soviet spacecraft. Got closer and closer. They continued not to be able to see anything but this dust cover. And once they went into orbit, the Soviet spacecraft expended all of its film photographing dust. Mariner 9 was reprogrammed from the ground, fortunately. Even then, JPL liked sequencing computers that you could program remotely from here. And it waited until we were able to see dust starting to clear out. And this is one of the first things that Mariner 9 was able to see. This is now known as Olympus Mons. It's a volcano. It's the tallest peak that we know of to date in the solar system, and about 27 kilometers above its base. The name Nix Olympica meant snows of Olympus. From here on Earth, it sometimes looks like it's covered with snow. It's actually cloud cover. In its photography mission, Mariner 9 also showed us this amazing artifact, a giant canyon system on Mars that's bigger than North America. And probably the greatest recognition JPL will ever get, I think, was the decision to name this canyon after these early robotic explorers. The canyon system is called the Valles Marineris, Valley of the Mariners. Unfortunately, though, for the believers in Martian life, they're reduced to hoping for microbes by this, Carl Sagan had hoped to find oases of places that life could live, but Mariner 9 photographed the whole surface to a resolution of a couple of kilometers. No oases found. So maybe they could be smaller than these oases of life that Sagan was hoping for could be smaller, but it didn't leave a lot of people with much hope in Martian life. However, it still left them with lots of interesting questions because of images like this. This has generally been interpreted as part of runoff system for liquid water, which could not be found in any of the Mariner 9 imagery. We didn't know where the water went, how a planet that could once have had an active liquid water cycle had ceased to have it. Obviously, that didn't happen on Earth. It's still active. But it left geologists, anyway, with lots of really interesting questions. But many of those questions revolved around the subject, again, of chemistry and climate. The Mariners revolutionized our knowledge of the inner solar system. They showed that planetary evolution was a lot more complex than we'd thought, that small differences in initial conditions produced huge differences in outcomes. Now, in a 1972 article, and here I'm just going to give you some examples of the thinking that was going on by the early 1970s about planetary climate evolution, Carl Sagan had speculated mathematically on the evolution of Earth and Mars climates. Astronomers, such as Sagan, believe that the sun was born much dimmer than it is now, about 30%, in fact. So that, in other words, Earth, Venus, and Mars should all have been getting hotter over their histories, instead of, as clearly happened with Mars, if you believe that that picture I showed you earlier is from liquid water, has gotten colder. So Sagan was trying to figure out how in the world you could reconcile a planet that cooled over time with a sun that warmed over time. And the only thing he could think of was the subject of climate and the greenhouse effect. And he tried to invent an atmosphere that would produce a large enough greenhouse effect on Mars to allow liquid water to have existed. Similarly, scientists interested in Venus were considering the issue of how in the world that place got so hot. This is an article by another NASA scientist at the time, Erik Conway, who I believe is now a senior official in the European Space Agency, investigating the subject of the runaway greenhouse effect and the accumulation of carbon dioxide in the Venus atmosphere. In fact, he was trying to figure out what you'd have to do to Earth to make it into Venus, which is kind of a horrible thought, I think. But again, he's interested in the impact of chemistry. What kinds of chemistry do you have to have on the surface in order to, and in the atmosphere in order to get that kind of reaction? This sort of subfield in planetary climate studies is sometimes called comparative climatology, sometimes comparative planetology. Here is a headline of an article from James Pollack, another one of Carl Sagan's colleagues here at NASA Ames Research Center in 1978, titled Climatic Change on the Terrestrial Planets. One of Pollack's claims to fame was his interest in aerosols. He did fundamental work trying to figure out what the Venus cloud layers was made out of, and was not the person who eventually proved that they were sulfuric acid clouds, but then went to work trying to characterize them well by looking at sulfuric acid in the Earth's upper atmosphere. That involved him, for example, in nuclear winter hypothesis that becomes very controversial in the early 1980s. Now, this planetary view even begins to encompass living processes and their effect on climate through atmospheric chemistry. James Lovelock, who worked here at the Jet Propulsion Lab in the early 1960s on instruments to look for life on Mars, became convinced that the place to look for life is not actually in the dirt, which is where most JPL people wanted to look and where the Viking missions did finally look, but in the atmosphere. Earth's atmosphere is unique in the inner solar system anyway, and that it's composed of gases that are unstable over long periods of time. That oxygen you're breathing is produced by critters, although this too was a minority view when Lovelock was writing these speculations, first with Diane Hitchcock and then Lynn Margulis, Carl Sagan's first wife. And it's led them eventually to conclude that life itself was responsible for the maintenance of Earth's climate. This very controversial view is called Gaia, after the Greek goddess of the Earth, and extended even to the issue of trying to figure out what the Earth's climate would have been had life not been here. This is what they came up with. The Earth would initially, starting from the very intensive greenhouse gas early atmosphere, should have cooled rapidly to the point that's about 3 billion years ago, and then slowly warmed as the sun did. But that's not really what's happened. Instead, this is about 10 degrees Celsius band. This is Lovelock speculating in the 1970s that it had actually stayed pretty much stable throughout this period he thought there was one big climate crisis right in this period about 2 billion years ago. And he thought that life's respiratory capabilities and its impact on the Earth's reflectivity were responsible for this relatively much more stable climate than stellar evolution theory implied it should have been. This view of Earth as a living, essentially self-governing organism was and still is very controversial, but it's a somewhat extreme form of a discipline NASA set out to create in the mid-1980s called Earth System Science, which is a study of biogeochemistry, the intersections of the biosphere, the geosphere, and the atmosphere. So I've been trying to beat into your head now this idea of chemistry and climate, so let me continue a little longer. In the 1950s, earthly geologists generally believed that there had been 4 great ice ages, several million years apart. That's because they could go out and date, relatively inaccurately as it turned out, the structural features left on the Earth's surface from the advancing glaciers, and that left them convinced that there had been these 4 great ice ages and no more. In 1969, however, there's a publication by a Dane by the name of Willy Danskoort of a paper that used gas bubbles trapped in the Greenland ice sheet to make a radically different argument. These gas bubbles showed that, in fact, the Earth's climate in the last 100,000 years has undergone many changes. Here is the last peak of the last ice age. You're looking at variations here in the surface temperature of Greenland and advance and retreats of the sheets. And then the post-glacial optimum here is our period of time, the last 10,000 years in which humans have existed. Now, initially, this is somewhat disregarded because, of course, it's only 100,000 years. It covers only one ice age. But in 1973, a tropical Pacific sediment core was analyzed in a similar fashion and showed a much longer record of glacial advance and retreats. In fact, it showed that the Earth's orbit cycle drove the ice ages and that there had not been 4, but many. That theory is often referred to as the Milankovitch theory after a mathematician, Milutin Milankovitch's work in the 1920s, but that had long been discarded precisely because these 4 great ice ages didn't line up with the solar cycle. The Earth's orbit cycles run in 41,000, 100,000, and there's a 19,000-year cycle, which all intersect to produce these changes. But it takes a number of years of further work to go back and redate all those glacial formations and to finally confirm that, yes, Milankovitch had been right. And these changes in gases that Danskoort had discovered in what's known as the Camp Century core had been instrumental in helping to drive these changes. Now understand that these orbit cycles produce only a very small change in incoming solar radiation. They, in fact, often produce no change in the total amount of sunlight that reached the Earth. They only change the distribution of that light across the surface. And that's enough through changes in the carbon cycle, in other words, the cycle produced by living things, to cause fundamental changes to the Earth's climate, triggering the advance and retreat of ice sheets. That's not a popular position in the early 1970s. It's quite controversial. Nowadays, it's widely accepted. And in fact, by the 1990s, the increasing interest in the subject of atmospheric chemistry, climate, and ice, it was becoming generally understood that humans have existed in a unique period of the Earth's recent history that was unusually stable. This headline on the right is from in the middle now, from the 1993 Nature article, whose point was that humans might be forcing the Earth's climate out of this stable state and back into an older, wilder form. The glaciologist Richard Alley at Penn State calls our climate a drunken, raging beast that's been sleeping for the last 10,000 years, and we're poking it with a stick. That's a far cry from the way climate was seen in the 1950s as stable and unchanging. So these questions of chemistry and climate remain powerful both scientifically and, as I think most of you know, politically. This is from the 2007 Intergovernmental Panel on Climate Change's studies. This I've actually ripped out of the chairman's summary presentation. This is our 650,000 year reconstruction of the Earth's climate history. Down here is temperature. These gray bands represent the periods of minimum glaciation, so they're the warmest periods. This is methane, which is a stronger greenhouse gas than carbon dioxide, but lasts a much shorter period in the Earth's atmosphere, decays in the matter of a few years. Carbon dioxide up here, and this is nitrous oxide, which is another greenhouse gas. Unfortunately, I couldn't find the explanation for why there's this big gap. But I show you this not to argue that all of this is true, but that this is an important and interesting scientific question. And I've wanted to connect the dots for you from Earth climate to planetary science. Now, from a narrowly scientific knowledge perspective, this revolution launched by the International Geophysical Year has been transformational. It's profoundly altered the way scientists see the Earth and its place in the solar system. But it's been transformative in other ways as well. NASA has become a leading scientific agency in its own right, with a space and Earth science budget as large as almost as large as the entire National Science Foundation. Now, I've discovered that not everybody knows what these various agencies do. The National Science Foundation here funds all physical sciences except space, and it funds a lot of facilities. It funds some, but not all, biological sciences, and it funds some social science research. NOAA here is the National Oceanographic and Atmospheric Administration. Most of its funding goes to run the Weather Satellite Center and weather forecasting operations. I was not able to find out how much of this budget actually goes to scientific research. This next column over here, of course, is the NASA Space and Earth Science budget, including satellite building. And I broke out NASA Earth Sciences to show you that it's really not, it's the tail wagging the dog in some ways. To look at this another way, climate science funding, since I've talked a lot about that. Here's the pie chart for who pays for what. NASA is the biggest slice of the climate funding pie these days. In fact, it has been all since the beginning of the 1990s. Most of this money, again, goes to building satellites. It's about $900 million a year goes to the satellite budget, and the rest goes to science. And I have one more. But lest I mislead you about the size of the climate science enterprise, I don't want you to think that it's like all of American science. Here on this side, my right, is the climate science spending versus all U.S. science spending, all civilian U.S. science spending. Vast majority of civilian science spending is the National Institutes of Health at about $25 billion. Climate science, you can see, is not even close to that. The far chart is total U.S. science and space science, just to show you how much larger a slice space science takes up. Now, we started this talking about the International Polar Year, so I figured I'd leave you with a polar picture. This is the American station at McMurdo, actually in 1987. One of the legacies of the International Geophysical Year I didn't talk about, but as kind of a background to this, is that there's a treaty negotiated signed in 1961 that makes Antarctica open to research, but not to territorial claims. So here's McMurdo is taken by a group of JPL scientists who went down to participate in the international ozone depletion experiment called known as the NOSE. And now I'm open for questions. Thanks. direction. Questions? Sure.
Are we in for a prolonged drought in Southern California, as Pat Surt, put on the paper the other day? So like 20, 30, 40 years, who knows?
Well, that I don't know. Boy, I hope not. Because let's see, I think it was a 29% worth of normal snowpack this year. That will survive another 2 or 3 years of that. After that, Southern California property is going to get real cheap. So I hope he's wrong. I really do. But I'm a historian, not a scientist, so I don't attempt to predict the future. Okay. Sorry. But that's one thing I hope the climate scientists are wrong about. I really do. Sure.
That chart that showed the correlation of the 650,000 years between the rise in CO2
Yep, there you go.
and the rise in temperature, do they know what caused the rise in CO2 or theories about what caused it?
The dominant understanding is that the changing distribution of sunlight, sorry, I should have repeated the question. The question is essentially whether we understand what causes the carbon dioxide increase that's clearly shown here, and thus brings this warming phase. The general understanding is that this changing distribution of sunlight on the surface changes the distribution of the growth cycle of plants, both in the ocean and on the land surface. And that produces the change in the carbon cycle. It's not understood in detail because, of course, there weren't humans around to measure all this stuff the last time it all happened. So that's one of the research areas that we'll probably never really understand. We do understand this part of it because this is the point at which we come along and start measuring things. One of the things Keeling did later in his career, and there were a number of people who worked on this as well, was to look at the carbon isotope ratio of current atmosphere carbon dioxide, the carbon dioxide trapped in these ice cores from the pre-industrial era, in order to show definitively that it's fossil fuel burning that's changing, that's producing this increase, and that it's not a natural function. And that work was all done by the middle of the 1970s. So I hope that answers your question.
Trying to correlate this graph with the other one that showed the most recent ice age from the ice core samples. Mm-hmm. It just seems like two graphs don't show the same ice age in the same time period.
I think that's an artifact of compression. Here we have 100,000 years. This reconstruction is a reconstruction from multiple cores, and whereas this earlier one, let me go back to it, is a reconstruction just from Greenland. So they won't quite match up because when you do a multi-proxy reconstruction, you wind up with a slightly different result. I don't understand the details myself. Again, I'm not a scientist. My point in displaying these was to get at this whole issue of chemistry and climate and how it becomes very interesting. I'd have to point you to one of the glaciologists here at JPL to explain the details of this, though.
If that's true, it seems like there's 90,000 band. There's a logarithmic scale of time on the right-hand side.
Yeah.
There's really 90,000 years of more ice, as I read that. From 100,000 years to 10,000 years ago is more ice.
And, right, and you have variations, too.
If you go to the
Yeah.
other one, then it looks like, if that's true, then more ice is the normal condition of the planet. This whole gap there
Yes.
of 90,000 years is the majority of time the planet has more ice, and it's only in the last 10,000 years we have
less.
nice.
Right. That's right. Because the deglaciation cycle begins about 14,000 years ago and then ends. Now, one of the things that interested everybody, and it has for a long time, is that the Earth's cooling cycle seems to take a lot longer than its warming cycle. It's a very asymmetric. And that's actually part of what's gotten people like James Hansen at the Goddard Institute for Space Studies, who's probably the most famous of the climatologists, worried about what we're doing because we're driving. These are natural variations that took place. Well, back here, my pointer is, I guess, running out of battery. That took place over thousands and tens of thousands of years, but we're driving this cycle much more rapidly. So will it respond more rapidly? And the answer is nobody really knows. But I know that there are a number of people. That's why Richard Alley talks about this being a drunken, raging beast. He thinks it will respond much faster than this historical record would imply. But yes, being glaciated has been kind of the normal state over the last couple of million years. Any more questions about the space race? Sure.
Big question about all the buildings built here. Where's the capital come from to build the buildings, and how come JPL is still kind of a department of Caltech, where it has an unusual, special relationship with the university? And is that normal? Like Ames doesn't seem to have that kind of relationship.
Yeah.
Is the unique relationship?
Yeah, it is. So the way that the relationship works for most, if not all, of what are known as the federally funded research and development centers is that the government owns the property. So JPL gets a new building when NASA decides we can have one. Well, I won't say any more about that. We get a new building when NASA says we can have one. Caltech actually has tried to pay for buildings here and got its fingers slapped for doing it. It was deemed illegal. So NASA owns the property. That's where that goes. The employees here work for Caltech. So we are considered the managers of the place. We get some amount of money to take care of it and so on. Within NASA, we're unique. We are the only NASA center like this. All the rest of the centers are civil service. We are not the only one federally funded research and development center, though. The Los Alamos National Laboratory, for example, is run by the University of California system. The Applied Physics Lab, our competitor on the East Coast, is run by University of Maryland, for the Navy. That's its primary patron. And all of us are governed by contracts which differ from agency to agency. That governs everything from the way we do our accounting to the kinds of stuff that we can publish in the open literature. In our case, it defines how much defense business we're allowed to do. It defines how many employees we can have. Not all the FRDCs are so tightly managed by the contract, but we are. But that's a legacy of the fact when we were set up for the Army, we were set up as a contract operation. The Army decided not to do what it usually does in this case. Usually the Army builds its own centers and runs them in-house. This is often referred to as the Army Arsenal System. Huntsville, the Army Ballistic Missile Agency, was an Army operation run by a general with von Braun's folks around as quasi-independent, but still under Army command. Sure.
During the International Geophysical Year, what were they doing in terms of polar research or things like that?
That's actually been a little difficult to disentangle. I just unfortunately encountered about 3 weeks ago the only history of that was just published last year of what was being done in Antarctica, and I'm only partway through it, I'm afraid. Basically, we and several other nations, I won't say how many because I don't remember the exact number, set up research stations, many of which were temporary, some of which were permanent, in order to, first off, map Antarctica. It had never been done, and to do this sorts of weather research that I suggested. Obviously, because McMurdo's still there are some permanent bases. The book I'm reading right now is called Deep Freeze, if you want to try to find it at a library. It's a fascinating story, really, of the development of the Antarctic research facilities, which is really interesting to read. But it doesn't, so far, it hasn't said much about the science. There has been no comprehensive history of the International Geophysical Year written. There have been some people who have tried to start, and apparently there are some ugly politics keeping them out of the National Academy's records. That's what I've been told by the archivist there anyway. So I can't tell you much else about what else is done because there's no other work. I'm the first person to talk about earth science, really. and planetary science in terms of the International Geophysical Year. And that's one of the reasons I set out on the set of papers. It's because it's a big historical whole. We know about the International Geophysical Year in the space race, and especially in the manned space program, but not about planetary at all, and almost nothing about Earth. Sure.
On the green line on that, why is it all cut into pieces?
Yeah, so that's nitrous oxide, and I don't know why that data doesn't exist. The way this chart's made, the organization that made it's called the International Governmental Panel on Climate Change, and it's a group of climate scientists that get together every few years to produce a survey of the field. What do they know and what do they not know? All right, and that's done by reviewing the published literature. So the fact that this graph has a big hole in it means that somebody hasn't got data for that particular substance in those bits of ice. Why they don't, I don't know. I wish I did, but it's not there in the material. And probably in order to find out, what I'd have to do is dig up the original papers that this report was based on. All right, that's how that process works. Go ahead.
Do you know what happened to the Russian space program? They were able to lift 2,000 pounds into space while we're lifting 25.
Oh, that's because, that's actually well understood. The Soviet nuclear weapons were much heavier, were much larger and heavier. Later on they were successful at miniaturizing them, but they weren't initially. So because they wanted those rockets to hoist the warheads, they made much bigger rockets. We were in a sense crippled because we were efficient. I hate to put it that way, but that's ultimately what it came down to. The Army and the Air Force both knew that Los Alamos had figured out a way to shrink the warheads down, to that big. So we didn't need those big rockets. Go ahead.
One of USC's former presidents, I believe it was Dr. Stephen Sample, was governor of Antarctica, and I believe there were 17 nations represented that got along well. Mm-hmm. And I'm wondering if there's still a cooperative arrangement going in terms of government.
There's certainly cooperative arrangements. The Antarctic Treaty is still in force, and it specifies arrangements, logistics, and so on. I know the United States, provide some emergency services down there. Both us and the Russians maintain active, for example, hospital facilities and so on. So yeah, the UN maintains the Arctic Treaty and performs the coordination functions down there. Yeah. Go ahead.
What did the IGY have to add to the plate tectonic theory?
That's an interesting question. As I said, since there's no comprehensive history, I don't know the answer to that. One of my colleagues published a history of plate tectonics. It cited the rejection of continental drift. Now, Harry Hess proposes the idea in an essay in 1960. He didn't call it even it was so ridiculous, he didn't even call it a theory or a hypothesis. He called it an essay in geopoetry. But in 1962, a couple of years later, is when Lamont Doherty comes up with the magnetic stripe evidence that I think lots of people have seen now for seafloor spreading. So I'm not aware of any direct connections to the International Geophysical Year, but they might still be there. There were oceanographic surveys undertaken during the IGY. In fact, they started well before, as doing a set of measurements in the oceans takes a very long time. There was an Atlantic Ocean survey started actually in 1955 for the IGY that's not finished till 1960. But again, I don't know whether any of that data is eventually used to aid in the development of the plate tectonics theory. Sorry. Go ahead.
How many nations were involved in the IGY? How many specific
40
experiments?
40 nations, but I can't tell you how many experiments. I would say it depends, first off, on how you define experiment. Is a single meteorological measurement taken at one point on time an experiment? Yeah, I don't know. I can't answer that question. Way in the back, go ahead.
How long would it take for the runaway greenhouse effect to take place on Earth?
Well, we don't know whether it would or not, I guess is what it comes right down to. Venus has had it because essentially all of its carbon is in the atmosphere, whereas on Earth, the vast majority of it now is buried. It's in rock units. And in order for it to happen here, you would have to get volcanism to remelt all those carbonate rocks and release the CO2. So it's not very likely to happen here. You would, I guess, a large enough meteorite impact might be able to release a lot of it, but we wouldn't live through that anyway. So hope it doesn't happen. But that's the best answer I can give you. It won't happen here simply because so much of the CO2 is now in a permanent storage form as rock. Yes?
Carl Sagan believed that in the universe there would be some form of life. For example, silicon life instead of carbon life. And I'm wondering if on any of the moons of Jupiter there is any evidence for any form of life.
So the question is, since Sagan believed in life elsewhere in the universe, is there any evidence on the moons of Jupiter or any place else in our solar system? And the answer to date is no. That doesn't mean it's not there, though. One of the really exciting discoveries of the late 1970s is the existence of these entire ecosystems around deep ocean vents. That has left some scientists with hope that you could find life underneath the ice sheet of Europa, one of Saturn's moons. Excuse me, I'm sorry, Jupiter, you're right. Getting my planets wrong. So you can see I study the inner planets, not the outer ones. Make a basic mistake like that. But whether it's true or not, who knows? There are people here who want to get missions to go look. How they do it, we think the ice sheet's like 16 kilometers thick. Antarctica's ice sheet is nowhere near that thick. So, and we just in the last 15 years have developed the ability to reach to the bottom of the Antarctic ice sheet. So getting through Europas and into the oceans from several billion miles away is quite a feat that we don't know how to accomplish. But it's possible. Sagan might be right. The way historians of science tend to look at this is there's kind of two factions in the scientific community. There's a faction that believes life forms very easily and will find it in lots of places. And there's a faction that believes that it forms only very, very narrow range of conditions, in which case we won't find very much. And I'm an agnostic. I don't know who's right. Go ahead.
What process here on Earth allows for this unique trapping of CO2 into rock?
Well, it's not unique. It just didn't. The belief is, and of course this is informed speculation only because there was nobody around to watch it 4 billion years ago, was that Venus was never cold enough for that process to start. Whereas Earth was, and we don't know yet about Mars. It doesn't. The thing that makes Mars interesting, of course, is that it used to have cold liquid water, as far as we can tell, but doesn't anymore. And that's a bit confusing if you accept, as astronomers do, that the sun has gotten warmer. But it's not a unique process. It's a straightforward geochemical one. For a long time here on Earth, that was believed to be the dominant means of removing CO2, and that the living process was slower. As I understand things, that's now reversed, and we think that the living process is the fast one. But again, it's not, because I've studied the atmosphere more, I haven't looked into the old hard rock geology. It's not unique, though. It's geochemistry, and we might find it on Mars. We haven't gone looking for carbonates yet. Well, that one rock from Mars that we think we found in Antarctica had carbonates. And it's an open question how they were formed. Any other questions? Sure.
Just on the next mission to Venus and Mars, is there arranging plan for Venus, and on the Mars, how come they decided not to do a rover on that one?
Oh, okay. So the Venus, the Europeans have a mission at Venus right now. We don't have one in the books at the moment. We, the U.S. the next Mars mission, Phoenix, is a rebuild of the 1998 Mars Polar Lander, which we lost. And, well, which we JPL lost. It was intended to land on the layered polar terrain, which is where we think where most of Mars's ice is, and to say, yes, it's really there, and to investigate one of the hypotheses that's about Mars, which is that its climate has shifted over time. They're hoping to see that recorded in layers and layers of ice. And that mission, the mission that's going this year, is a rebuild of that because NASA has decided to compete every other launch opportunity to Mars. And this was the winning repeat, largely because a lot of the hardware was already built. There was a mission there was supposed to be a lander mission in 2001 that was canceled after we lost the polar lander. And that's hardware is the basis of what's called the Mars Phoenix mission. But that's why it's not a rover. It was never intended to be one. The 2009 mission is a rover, a Mars Science Lab, big rover. So that's what'll be going up next. Go ahead. How did we lose it? Oh boy, that's a complicated question. Basically, it was inadequately tested. That mission took place at the height of what's known as the faster, better, cheaper era in American space program, in which we were supposed to, and actually are mostly spent on a contract to Lockheed Martin in Denver. We were supposed to deliver 2 spacecraft to Mars for a total of about $180 million. And I guess the short answer is that's not enough money. So they didn't do tests that they needed to do, in retrospect anyway, to verify that the design really would work. There is an investigation board report that blames the loss on a bit of software that was supposed to cut off the landing rocket at a specific point when it was much closer to touchdown. And at that time, they thought that this software shut the rocket off too early, and so that the thing sort of plummeted the last 60 meters or so. We don't believe that anymore. We've discovered a number of other faults in the Phoenix design, and in that design, in the 98 design, and have corrected them. And we'll find out in about a year and a half whether we got them all. Yes, go ahead.
You're a historian and you look backwards, not forward, but could you make an exception and tell us what the future of JPL will be?
Well, we hope it's continued planetary exploration. About a third of our business is Earth stuff, in terms of money anyway. We have groups that do some Antarctic and Arctic work. We have a strong group that does ocean surface altimetry, it's called, for measuring sea level rise and things like that. And we all hope that continues. The drawback that JPL faces over the next few years is the NASA budget is going to get very, very tight as their new human-rated rocket comes online and they start doing the manned missions, they hope, beyond Earth orbit. For JPL, that can be a budget risk because those overruns could eat our budget, but we all hope not. But that's the best projection I can make for you. We don't. I'm not aware of any intention in our leadership to suddenly try to change direction for the lab again. They all love what we do now. It's great stuff, and usually this room is full every month of people wanting to hear the latest news from the planets, from the Spitzer Space Telescope people and those sorts of things. And so do I. I'm a frequent attender of these lectures, usually sitting in the back, and not up here. Anyone else? Sure.
How is that New Horizons project going so far? Yeah, the Pluto.
Yeah, so far as I know, that's not a JPL mission. It's important to know. It was the PI is now the new director of space science for NASA, Alan Stern, out of the Southwest Research Institute, I believe, is where he hails from. And the management for it was done jointly, as I understand it, by Southwest and by Applied Physics Lab in Maryland. So as far as I know, it's going fantastic, but I have very limited contact with the project. So that's what I know, sorry. Yeah.
When they talk about the polar ice caps on Mars, are they referring to water ice or CO2 ice?
Actually,
I would imagine it's water.
It's actually both. There is a seasonal ice cap that's CO2, and as the seasons, as they get Martian summer, the CO2 evaporates and exposes the water. The water ice. That was a bit, that was confusing. A lot of people assumed in the early planetary exercises that whatever ice cap they found would be stable, but they kept getting anomalous readings. Sometimes they get the temperatures that would equate to CO2, and sometimes they would get water, and it left them very confused until they realized it could in fact be both. And it is. It's both. Go ahead.
The early observations of Mars saw seasonal changes, which they interpreted as vegetation. What is that they were seeing?
Well, that's actually only recently been looked at, and they think that albedo change has to do with the presence of this carbon dioxide and water ice in the upper surface soil. The Mars Odyssey mission, the 2001 Odyssey mission, demonstrated that there's water ice throughout the first upper meter of the surface. It can't measure for CO2 ice, but simply the seasonal melting and, well, not really melting, sublimation is the correct term for transition from a solid state straight to a gas, is probably responsible for that albedo change. But that's only it's a very recent article, maybe a year old. I forget who the author was. But that's what we think now. It may change. Go ahead.
Is it possible that it could have been a runaway process of the storing CO2 in rock that caused Mars to get so cold?
Don't know.
I know.
Sorry. It's possible. I mean, we know so little about early Mars right now. We've the two rovers that are there now doing geology are in the Martian tropics, in essence. They're in the warmest part of the planet. So that doesn't tell us much about what might have been going on at the poles, and they can't get below the surface either. So we know very little bit about the Mars surface chemistry, and that's about it. Go ahead.
I heard that the new rover that's going to be sent up there can dig into the ground, and how deep can it go? Because if it goes deep, you said that there was ice under the surface. Mm-hmm. Will the new rover that they're sending up, will it find the ice that's under the surface that you said?
Yeah, it has some ability to dig. It doesn't go very deep. What we're interested in getting, as I understand it now, I'm not. It's being built here, though. I don't have much connection to the project. There's some belief amongst people who still believe in life on Mars that if you can get below the first half meter or so, you might be able to find evidence of organic matter. The reason we don't find it above that is that the solar ultraviolet flux is so strong it blows apart organic molecules, large molecules. So if you get a little bit below that, then you might be able to find evidence of organic materials. And they almost certainly will find water ice. But it won't be a solid layer. It'll simply be mixed in with the soil. So they should be able to find those things. That's what they're hoping to find anyway. But yeah, so it'll get down to a half meter or so. I don't know the exact number, so don't quote me. It's not I know exactly who's developing that instrument and what exactly it will be able to do. But it will have the ability to measure things like water and organic materials and so forth, should it dig any up.
Is the
Go
high
ahead.
radiation caused by not having a magnetic field? Do you have any history of, did it used to have a stronger magnetic field and now it doesn't?
Mm-hmm. Okay, so the question is, did Mars does Mars have large radiation because it has no magnetic field? The answer is yes, it has no magnetic field. That's part of why it has such a high radiation flux at the surface. The ultraviolet flux comes from not having an ozone layer, and it doesn't have an ozone layer because it hasn't got any oxygen in the atmosphere. It's 99% CO2, and then there's a percent that's argon and some other inert gases. Mars, however, used to have a magnetic field. Nobody knows what happened to it. There's some very interesting results from the Mars Global Surveyor mission that it was actually a very, very strong magnetic field, much stronger than a planet that size should have had. So there's lots of people wondering why that was too, as well as the what did happen to it issue. And the simple answer is we don't know. We don't have enough data. It is a good question. And let's see, it's 8:30, so almost 8:30 anyway. So I guess I'll take one more question and then call it done. Well, maybe I won't take one more question. Oh, okay.
Regarding global warming, I think there's still a question whether the CO2 and the temperature, which one's the cause and which one's the effect. Obviously, in your 650,000 year graph, the CO2 spiking recently has not resulted in a spike of temperature right away.
Well, not right away. That's
not a correlation immediately.
Right. So there's about a. Go ahead.
So, has anyone actually excluded the possibility that simply internal friction of the Earth creating more vulcanization, releasing heat actually from more volcanoes, more lava, than has ever been in the history or in the last 100,000 years? That's actually internal heat coming out to heat the atmosphere. And that is what's causing the heating, and then therefore CO2 is the result of that.
Yeah, we do know that. The rate of volcanism's going down, not up, over long periods of time. And there have been much more active periods of volcanism in the Earth's history, the Deccan Traps volcanism, and so on. So there actually has been an increase in the Earth's temperature. There's about a 30-year lag in the climate system. And so CO2 emissions, we're seeing the temperature increases now from CO2 released cumulatively from before the 1970s. And that's part of the policy problem. What do you do about something that's so far in the future? As I said, because we've determined the isotopic fractions, we know that the CO2 is from fossil fuels and not from what could otherwise be perceived as a natural shift in the carbon cycle. So all that work has really been done. One of my backup charts, since we closed this up, I can't show it to you, is actually of solar activity over most of the last century. And so we actually know it's also not from an increase in solar output. That leaves us with about 90% of it being, of the temperature increase we have seen being from greenhouse gases, and we figure about 10% from, that's potentially from internal natural variation. Another one of the charts I can't show you is Hansen's examination of what the limits of natural variability, short-term natural variability in your system is. And he figured that by the middle 1990s, you would actually be able to determine whether global warming had exceeded that level, and anthropogenic warming had exceeded the level of natural variation and thus become a unique signature. And the IPCC's analysis is that he's essentially right. It was visible by the late 1990s in the temperature record.
Why is there a 30-year delay?
The thermal inertia of the oceans. Water absorbs an enormous amount of energy before it goes up in temperature. Much more than rock does, and certainly much more than the atmosphere does. And that thermal inertia has the effect of masking a surface temperature increase for a while until the ocean starts releasing that temperature, that heat, in the form of increased evaporation. And the increased evaporation carries that energy into the atmosphere, and then we can measure it as a surface temperature increase. Another one of the shocks that I didn't get into is the belief in the 1970s that ocean warming would not even be measurable from this CO2 increase I've talked about for hundreds of years. There were some oceanographers who didn't think it'd be measurable within 1,000 years. It was first demonstrated in 1999. And that actually brought aboard that and a couple of other reanalyses over the next two or 3 years after that converted most of the oceanographic community from disbelievers in global warming to believers. So it's fairly recent. That's also one of the reasons you've seen such a coalition of interest in the scientific community. The atmospheric people expected to see it long before the oceanographers did. And I guess that's done. Thank you all for coming.